I'm Qianyi. I am a PhD student at UC Davis working with Max Rudolph, and today I am excited to tell you about how do I use VR to trace mantle plumes from global seismic tomographic model. So because today is a visualization focused talk, so I will not focus on the science part of this project that much. But if you're interested in the more plume part, science part, all the material that I'm presenting today, you can find that in our paper we published on GCubes last year. So before we get into the talk, I would like to give you a brief overview of today's talk. So first, I'm going to talk a little bit about why do we need to know about plume shape quantitatively and systematically. And then I'm going to talk about why virtual reality is essential to this study and how the work was actually done. And then I will present you some qualitative and quantitative observations of the plume that we traced. And I will conclude the talk with talking about some implications of our findings, the dynamic implications of our findings. So mantle plumes, as we all know, there are some hot upwelling developed from the core and mantle boundary from some instability. And the head of the plume, as they're ascending to Earth's surface, they're forming the large igneous provinces. And when the head has been disappear, you're left with a conduit, which produce the hotspot that we see on Earth today. So a conventional viewpoint on mantle plume suggests that a plume are supposed to have a kind of narrow conduit, which is about 100 to 200 kilometers wide, and have a very large spherical head on the scale of 1,000 kilometers, as you can see from this image of lab of plume material back in 1989. However, the state-of-art global seismic tomographic model have successfully revealed many bot plume, which means the conduit of plume, which you can see from on these two figures, which is this slow VS anomaly, negative VS anomaly. Here you can see the conduit, instead of being very narrow, they're actually pretty broad on the scale of 800 to 1,000 kilometers wide. So not just this plume, so just to give you a better idea of what the distribution of this bot plume on Earth mantle. In Earth mantles, I'm here showing you a map view. So on the map, the base map are showing you the VS anomaly at the core mantle boundary at about 2,800 Kelvin depth. And on top of it, you see that all that little kind of circle over there, and they represent the surface locations of the hotspot on current date Earth. And you can even see that there is some plume that are claimed to be primary and clearly resolved. They are the plume that claimed by global tomographic model SEMUCB-WM1 that they have been fully resolved in the mantle. And you can see that plume, rather than just distributed randomly on Earth, they're kind of like clustering around or inside this what we call the two large low shear velocity provinces. So they are just some some slow VS anomaly provinces, continental scale provinces that located at the core mantle boundary, and one of it sit beneath the Pacific Ocean. Hopefully you can see this is the Pacific, and the other one sit beneath the Atlantic and African. So that's the other one, and you can see the plume is clustering around them. So I'm not going to talk too much about the LSVP here, but you're going to hear me referring to them in this talk. So you have an idea where they are and what they may look like. So this interesting plume shade that we see from global tomographic model could tell us a lot about the mantle viscosity structure, the mantle flow field, the potential mineral phase transitions that may occur in Earth mantles, as well as the potential plume compositions differences between plume and its ambient mantle. However, despite we already have some global tomographic model that have resolved this interesting plume shape, there has not been a systematic catalog for plume shape. And yet, and this would become a problem for the geodynamic modeling community when people are trying to compare the plume shape that they predict from their model with some real seismic observations. So previously, when people are trying to compare, they can either just like compare it for an individual plumes where they have good regional model for that specific plume, for example, on like Yellowstone and Hawaii, or they just end up predicting a lot of great plume shape from their model, but they don't know if those kind of shape actually exist in Earth mantle, or which plume may have the shape that they predicting. And this lack of systematic viewpoint of plume shape could also be a problem for the geochemist community when they're trying to link the isotopic signature like the surface distributions of different geochemical signal to deep mantle reservoir. So here, for example, here showing an example where geochemists are trying to link the isotopic signatures of the oceanic islands in the Pacific region to different deep mantle reservoir via plume conduits. However, the conceptual model they have for plume conduit, which is shown in these two schematic pictures down there, are definitely oversimplified. And this conceptual model are not based on any seismic imagings of Earth mantle. And you will find out in the talk later, very soon, that the plume in the Pacific region looks nothing like what this conceptual model have shown. All right. So you did what's going on? Okay. So then you may just ask a question. Okay, so we have good global seismic tomographic model that have resolved fault plume. So why not we just take the conventional approach, just making a couple of cross sections across hotspot on Earth, so that you can look at the shape of plume and you get a overall idea, and you can build a catalog of them. This turned out that visualizing plume in cross sections have its own limitations. It's because plume are 3D structure, which means they can either extend inward or outward to the plane of the cross sections. Here is an example. So can you see my cursor? Okay, yeah. So here you are looking at a map view of the Pacific region, and east is on your left-hand side, where west is on your right-hand side. So you're kind of like viewing it from north to south. And here you can see that there is a couple of colored worms. They represent a pathway of the trace conduit, and the color scale stand for depth. And you can see a couple of the locations of many hotspots in the Pacific region. And here you're looking at a cross section taken from SEMUCB-WM1 along this line A and A pi. And here is the cross sections, and you can see that there is plume conduit beneath Pitcairn, Tahiti, and Samoa. And it seems like if you look at here, it seems like the conduit below Tahiti are kind of disconnecting, kind of disappearing in the upper mantle. If you only like this part, like there's not much like slow yellowish reddish thing down there. So you may think, oh, the conduit are either just becoming very small, so invisible in the upper mantle, or they are just kind of disconnecting. However, if you look at the same region, but now from a 3D viewpoint, like down here,
Qianyi,
like what? Yeah.
sorry to interrupt, but what I'm looking at is limitation of visualizing plumes in 2D. That's the title I'm looking at. And I think you're pointing to something else, but
Oh, wow. Do you see my cursor?
I see your cursor, but when you're, the title of the slide is limitation of visualizing plumes in 2D. Is that
Yeah.
correct? Oh,
Yeah.
okay. Okay.
Yeah. Sorry for the confusions. And yeah, no, I'm just, can you look at like something? Okay, cool. Yeah, so what I'm trying to show in this figure is that, so now you're looking at the same region, same tomographic model, but now you are looking at the isosurface of different VS anomaly. So here, this yellow one, this yellow isosurface represent a VS anomaly of negative 0.75. So, which basically, yeah, the color scheme mean the same thing. So here, if you look from a 3D viewpoint, you will find that the plume conduit beneath Tahiti, which is this part, they are, instead of disappearing in the upper mantle, it just extend into the plane and then rise up again and connecting back to the surface. So then the other question, the following up question will be, okay, so just as what you have shown us, what I've just shown you, I can look at the tomographic model. So why not? So why not you just divided those tomographic model into several blocks, so you can just look at them one at a time, like this one that I just showed you, so you can still get a good idea of what the plume shape in 3D. So why would you need VR? Why can't they just be done on a computer? So there are many specific challenges for tracing plume compared to tracing other things such as slab. So first, we only know where do the plume conduits start, which is they are surface hotspot locations. However, as the plume conduit get into the upper mantle, it can be either highly tilted or you can find kind of more than one possible slow conduit-like structure around one surface hotspot, and then how do you decide on which conduit, like which path should you follow? It's kind of very different from where you're trying to find a slab from a tomographic model around a trench. You're not going to find kind of two slab-like structure in the tomographic model that are close to one trench. And then second, it requires a lot of experimenting with different VS anomaly isosurface to determine which value would give you, which values of isosurface would give you a shape that best represent the plume. So I'll give you an example in a minute so you understand what this point actually means. And third, when you look into those plume cluster, usually at the center part of the LSVP, you will find that the isosurface that define the boundary of different conduits usually obscure each other. It making things very tricky to identify which is which if you are only looking at the model from the outer sides and not inside. You see. So here is an example. So here I'm showing you a 3D isosurface views of the same Pacific plume cluster region, but this time instead of knowing exactly choosing a VS, an isosurface of VS anomaly point negative 0.75 and negative 1.2 and negative 2%, I am just randomly choosing some negative VS anomaly value and plot their isosurface. And this is what the model now looks like. So now you can no longer see the clearly like the well-defined plume conduit from in this model if you're only viewing this trunk from the outer side. And VR could help us to overcome this obstacle because it will actually allow you to kind of walking into the structure and looking at the slower the isosurface with a more negative VS anomaly value inside this kind of like wrapping surface layer. So hopefully by this point, I have persuaded you that VR actually play a very crucial role in extracting geometric information out from 3D dataset of Earth's interior. So then to be able to trace plume, we of course need to come up with some reasonable criteria for it. And here is the criteria that we used based on the thermal characteristic of plume. So we want our conduit first to be hotter than the surrounding, and we want it to be continuous across most of the mantle, And then we also want the VS anomaly along the plume conduit are kind of consistent with the petrological estimated plume assessed temperature. And I will give more explanation to it as we get to the result part. So we traced 20 plumes, what we think is clearly resolved and kind of primary plume and supposed to originate from deep mantle from two full waveform inversion global seismic tomographic model. One is SEMUCB-WM1 and the second is the VS, the shear velocity part of the GLAD-M25. And I'm not going to go too much detail about what full waveform inversion global seismic tomographic model means. But basically, the key idea is that only this full waveform inversion model are able to resolve plume at a global scale. So that's why we're choosing them. And then this VR visualizations are done at the KK Data Visualization Lab at UC Davis, and it's used to be like a real cave with 4 projectors, and you kind of use it with 3D glasses and controller. But now things has been upgraded to VR headset, which are more accessible, easier to set up. And here's an image showing how I was doing my work. So I'm wearing my headset, I have controller in my hands, and I have 2 lighthouse that are tracking my head and hands motion. And on the screen, it's kind of showing what I'm looking at from my headset viewpoint. And this VR visualization is done in ParaView using ParaView's nice XR interface plugin. So ParaView first is like an open source software, and this VR plugin is extremely easy to use. So first, for whatever data you normally visualize in ParaView, you can just automatically visualize it in a VR environment with this plugin. No extra coding or data reformatting is needed. And then ParaView also have a great tutorial online teaching you how to use ParaView in a VR interface. And also, this plugin supports most of the mainstream VR headset, such as Valve Index, HTC Vive, and also I think also they support the Meta, the brand from the Meta company. So you can basically whatever VR headset you have, you can just use them with this plugin, and that's very nice. So then I'm going to show you a couple of videos showing what my view when I'm using the VR ParaView in a VR environment to visualize my data, and what kind of tool and what kind of things you can do with it. So first in VR, here, hopefully you can see this is my tomographic model, and I am holding my controller. So the first thing you can do is definitely like rotating the data, so you can look at them from different part of the data. And then the second thing you can do is you can also like move the model around so you can view at it from different angle. And then the other things you can always do is also zoom in or zoom out from your data. It will allow you to make the model extremely large. So you can kind of, rather than looking at the tomographic model from a outer viewpoint, you can put yourself into the mantle, and you can literally stand at the core and mantle boundary and look at all the cool plume structure or slab structure if you're interested in slab. So that's pretty cool. I'll show you the view in a minute. And then there is 2 very useful tools that I use to observe my tomographic model. So the first thing is called the interactive corp. So here in the video, you're looking at the kind of VR, the panel of ParaView in a VR environment, and you can just select your right trigger approach to be interactive corp. And with this tool turned on, you can now cropping or slicing through the model in real time as you moving your controller and holding the trigger, and this is what it looks like. And this tool could be very cool or very useful, especially when you zoom into your data and put yourself into the mantle. So this interactive curve will allow you to kind of seeing through whatever kind of slower structure that hidden within this kind of faster or like less negative VS anomaly isosurface. And yeah, this is the viewpoint as you enter the Earth mantle and looking at everything. And this is the core mantle boundary. Yeah. Yay. And yeah, and this is how it looks like if you standing inside the mantle and using the interactive curve. And then the other thing that you can do is instead of using this interactive curve, you can actually just add a crop plane in VR, just like the normal way that you slice your data in ParaView on your desktop. So here now you're having a crop plane, and you can just use your controller to grab it and change its orientation and place it everywhere, anywhere you want, so you can have like a more stationary, stable viewpoint of different part of the model that you are interested in. So with this, with the help of this two useful tool, I'm then able to trace plume conduit. So first, so here I'm showing you an example of how I trace a plume right there. It's Samoa. It's okay if you don't have any geographic information of it, but you have to believe me, this is Samoa. This white little ball represent the surface hotspot locations of it, and this is where we know the plume conduit start. So first, you would need to find the plume structure around this hotspot. So here is how it was done. So after placing the crop plane, you can see, okay, so this part, this yellow part, it looks like the plume structure that I'm interested in. So, and then after that, I would like to place my crop planes right through the center of the conduit, because it would make sense if when I'm tracing a conduit, I would like to trace it through the center of the conduit instead of like tracing through the side of it, right? So I'm trying to slice through the center, which means like slicing through the slowest part. So like what I'm doing here. Oh, sorry. Oh, sorry to look at the same video again, but. Oh. But this is the central part of the plume conduit in most of the mantle. And this white little one or string of whiteboard here are the trace conduit of this plume. I put them up just so you can have a sense of what the trace conduit may look like in the tomographic model. And if you pulling in, zoom into this region and look at this plume structure closer, you may see that, hopefully you can see that this plume, the surface hotspot location, are actually not in the same plane as the lower, as the mantle part of the conduit. At this point, it's kind of behind the plane, the crop plane that I have here. And I don't know if you can see it, but actually there is some part of this conduit are actually like the shallowest parts of the conduit are actually outside of this plane. So to be able to also trace that part, I would need to add another crop plane in. So I would still be able to like look at the other part of the conduit. So sorry if I confuse you, but the point of the takeaway is just because plume conduit are 3D structures, so sometimes you would need to add two crop plane across all the center part of the conduit that may sit in different plane, so you can trace them. So, so with this nice tracing, like with this proper slicing or cropping of my tomographic model, now I'm ready to trace it. So the way that I'm trying to trace it is by adding some point along different part of the conduit. So I would get a line that representing the plume, the trace plume conduit. And here, and this work is done by bringing everything back to a computer screen. So here you are looking at a view on a normal ParaView desktop interface after applying those crop plane in the VR interface. So hopefully it makes sense. The SEM trunk is slicing like that. And there is one thing that very nice about the ParaView VR interface is that whenever you add a crop plane in the VR interface, it automatically apply it to all the data that you show. So instead of like versus if you only using ParaView on the desktop, if you would like to apply the same crop plane to different data, you would need to apply it like one at a time. So it become very handy for my cases. And here is why. So when I'm trying to place those points to represent a plume conduit, I am trying to add point every 200 kilometers radically. So just as a geologist, when they're trying to sampling across some formations, you would like to sample like every 100 meters. So you are making sure that you are sampling that kind of formations or whatever unit properly, and you are not biased, like you don't have any spatial bias. So to be able to do that, I would need to have some reference. Depth reference in my model, and I do it by adding multiple spheres with different radius. I don't know if you can see it, but this is the spheres with different radius. So I can know, oh, so whenever I'm adding a point, I'm trying to add a point right at those spheres. So I can do that, so I can fulfill this requirement. And with the help of the VR interface of ParaView, I'm able to just cropping everything at one time. So whenever I need to slightly change the orientations of my crop plane, so I will be able to better see my conduit, it will done automatically in VR versus if you're trying to do it on a desktop version of ParaView, you need to apply it all again to all the spheres you have here. And you can imagine how time consuming it would be. So, and back on the computer interface of ParaView, you can select and add point, you can remove point, and you can move those points up and down and in and out, etc. So with that, you will be able to place the conduit, you will be able to trace the conduit properly. So with all the help of ParaView VR plugin, the total hours that I spent on observing and tracing 20 plume from 2 global tomographic model is about 180 hours. So you can imagine without the help of ParaView VR plugin, how more time consuming this project could be. And I would even argue that without the help of VR being actually looking at the data in a immersive VR environment, I would never be able to have an understanding of what the plume may look like, and this work will never be able to done. All right. So after tracing all the plume, we have all the great trace plume conduit. We now want to make some quantitative measurement along the conduit, and we would also like to compare this quantity or properties along the conduit with other conduits, with the model conduit, which is predicted in Sternberger and Tartar 2006, and also with the vertical conduit that right beneath the hotspot. So we evaluate the slowness, which is represented by the VS anomaly along all the conduit, and we measure the tilted angle, as well as measure the lateral offset and azimuth of the conduit with respect to its surface hotspot, and I'll explain it more later. So first, let's look at an overview. So here you're looking at a map showing you the VS anomaly in SEMUCB-WM1 at the core mantle boundary, and this is the color scale of VS anomaly. And here the colored worms, they are representing the pathway of the model conduit from the Sternberger and Enter 2006 model. And this grayscale worm that represent the pathway of our trace conduit. And as you can see, some of the trace conduit and model conduit, they kind of agree with each other like this, like here, and maybe this one. But for a lot of other plumes, the model conduit and trace conduit differ a lot from each other, especially for Hawaii here. And then we do the same thing for the conduit that we trace from GLAD-M25, and you can see similar conclusions still hold. So for some plume conduit, the trace conduit agree with the model conduit, but for some others, they kind of looks very different. So here is an example showing you how the slowness along a plume conduit will look like. So here you're looking at an example for plume Hawaii. So here on the left diagram here, you are looking at the slowness across the trace conduit from SEMUCB-WM1 when they're evaluating in SEMUCB-WM1. And this is and the blue line represent the slowness of the model conduit, and the yellow line represent the slowness across the vertical conduit. And what you can see is our trace conduit are much slower compared to the model conduit. They may, and also like slightly slower than the vertical conduit. And similar thing for also for the trace conduit from GLAD-M25. So our trace conduit are slower than most of them. And also you see there is a blue shaded region also in this graph, and they represent the expected VS anomaly given a positive 200 Kelvin to positive 500 Kelvin temperature deviations from mantle adiabat. And this gray line here, they represent the expected VS anomaly given a assessed temperature of 290 Kelvin, which is the petrological estimations of the assessed temperature of Hawaii. So as you can see, like, yeah, so you just have a sense of how does like the, yeah. I don't want to say more about this. And after doing this analysis for our individual plume, we then compute the average slowness of all the trace conduit, vertical conduit, and model conduit in both model. So here on the left panel, you're looking at the average slowness result from SEMUCB-WM1. And again, you find that our trace conduit, which is this red line, are much slower than the vertical conduit and the model conduit. And the same conclusions also held for the trace conduit from GLAD-M25. And this is good because we know that plume are slow structure, slow VS anomaly structure. So the slower, the more negative our trace conduit is, which means it's better represent plume structure. So the slower, the better performance. So just to further validate our model, we're now evaluating all the trace conduit that we trace from at SEMUCB-WM1, and we now evaluating them back in GLAD-M25, and we evaluate the conduit we trace from GLAD-M25 in SEMUCB, so WM1, so we know that we could have a sense of how the trace conduit to see if the conduit that we trace from one model still valid or still slow in the other tomographic model, which based on very different conceptual model and yeah, etc. And as you can see here on the left panel, you can see our trace conduit from SEMUCB. When they're evaluating GLAD-M25, they're still slower than the model conduit and vertical conduit, at least in the lower mantle part, and the same thing for conduit we trace from GLAD-M25. And this is good. That's telling us that at least the pathway of the conduit that we trace in the lower mantle, they're not just some artifacts and like something that's only true for one model, but will not apply to the other tomographic model. So to further test the robustness of our trace conduit, we then just extend this cross-validation process by evaluating the trace conduit from SEMUCB-WM1 in all these other global tomographic models. You don't need to look into too much detail, but the key, and the same thing for the trace conduit from GLAD-M25 as well. And the key idea is that our trace conduit are still slower than the model conduit and vertical conduit in the lower mantle. So which is the region that bound by this dashed line, like here, 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 and here. So that's good. That's telling that, okay, we have some certainty of the robustness of the conduit that we trace. So then we look at the shape of the plume quantitatively and qualitatively. So first, and I'm going to give you an example of one plume reunion. So here you're first looking at, again, a map view. And on the map, you can see the trace conduit path wave from SEMUCB. And here you're looking at a cross-section taken along this line from SEMUCB-WM1. And here is reunion. You can kind of see that this conduit is starting here and then going a little bit northeast and then going back to southwest. And here is the more quantitative measurement of it. So here on the left panel, you're looking at the azimuth of this trace conduit, which is represented by this solid line with the closed circle here, and the distance away from the surface hotspot locations, which is represented also by this solid line with closed circle. And just for comparison, we also do the same measurement for the model conduit, which is shown by this thick line here and here. And one observations you can make is our model conduit tend to have like a much smoother path in the mantle. So the directions of the conduit, although like the distance away from the surface hotspot is increasing, which means the plume is tilting, but the tilting directions do not really change. Versus our trace conduit, there is a lot of variations in the conduit directions from upper mantle to the lower mantle. And just to also add in the result for the trace conduit from GLAD-M25, which is represented by this dashed line with open circles. So again, you see there are small variations in plume conduit directions in the upper mantle. So generally, this kind of observations that our trace conduit tend to have like meandering more in the mantle compared to the model conduit, which is usually just some tilted line in the mantle. And this observation is it's true for almost every plumes that we trace and look at. So after look at all the behavior of our individual plume, we find a variety of complex plume shapes. So first, we see plume pounding at 410, for example. Samoa in SEMUCB-WM1, you don't really see. So this part is the pounding at 410. You don't really see this in GLAD-M25, and I'm not going to go into too much detail about that, but it's possible that there is, because of the different kind of parameterizations, difference between these two tomographic model and causing that like this thing only show up in Samoa. But then we also see plume pounded at 660 kilometers, for example, the cases for St. Helena. Here, hopefully you can see the plume is pounding right below 660, and it can be seen in both model. And we see the deflections of conduit very often in the upper mantle. For example, Samoa, you can see the conduit is deflected at 660. And for sure, St. Helena's, they get deflected here. And this deflection could be hinted or can be seen by the tilted angle that we measure along different plume conduit. So here you're looking at the tilted angle along the trace conduit of St. Helena's, and you can see a large tilted angle right at the 660 kilometers depth, which tell you that there is a deflections there. And then we also see plume pounded at some deeper depth. For example, if you look at plume, Cape Verde, and Canary in SEMUCB-WM1, it seems like this plume are kind of pounding at a depth deeper than 660 kilometers, and you can But if you look at GLAD-M25, you may say that this plume is pound at 660, depending on what you're looking at. And then again, we see some secondary plume that develop from the pounding region and then rise up to the surface. So here, you looks like there is two hotspots here, and there is some board plume structure in the lower mantle, but it seems like you're missing the conduit in the upper mantle. That could be the sign of you're having like more narrower secondary plume conduit that develop from this pounding region. So they're so narrow that they're not resolved in the upper mantle, but they're there and still rising up and connecting. And if you are measuring the tilted angle along those conduit, you will find some large tilted angle at the pounding depth, which indicate that your secondary plume is kind of deflecting, like lateral drifted. So finally, let's come down to amateur dynamicness. So let's talk about some dynamic implications here. So first, the interesting plume pounding behavior happened at a 410. It may explain by some compositional difference between the plume and its surrounding mantle. So for example, in Lemberg and Solobalov 2015 paper, their numerical model work proposing that if a plume could have some eclogitic material in it, the density difference between the eclogite and ambient mantle rock, which is usually pyrolite, will make a buoyancy barrier at 410. It will stop the plume from rising and forming some pounding region at the 410. And then for the plume pounding at 660 and the deflection conduit that we see for St. Helena's in both model, it could be a result of plume pounding. So for example, in Tosi and Yuan 2001, their model show that because of plume pounding, because of the phase transition from ringwoodite to bridgmanite happen at 660 kilometers, you are able to pound some plume material at that step. And because you are accumulating a lot of hot plume material right at that step, you are reducing the viscosity locally. So you end up forming some channel flow right beneath the 660 kilometers depth barrier. And with some help of maybe some mantle flow, then your plume conduit are able to get deflected and then rise again to the surface. So, and then for the case of Cape Verde and Canary, where you have some border primary plume get pounded at some depth and have some narrow secondary plume develop from the pounding region, Liu and Lung 2020 kind of propose give some model, kind of give some hints of how you may form this type of plume shape. So first, you pounding some plume material right beneath 660 kilometers due to the same phase transitions, ringwoodite to bridgmanite phase transitions. And then if you then have like a layer of very low viscosity right above that pounding region, you're highly increasing the mobility of that region. So you will allow multiple secondary plume that kind of develop freely from that pounding region, and they may, and then they will end up with this large lateral deflections that we see in the tomographic model. And moreover, for those very interesting suspicious plume pounding that may happen at the 1,000 kilometers for some plume, but only happen in SEMUCB-WM1, not in GLAD-M25. Some possible dynamic explanation to that could be that it's proposed by this paper, Xiang et al. 2021. So what they're proposing is that if you are having a lower mantle that are more enriched in basaltic material or eclogitic material, you will end up have a denser lower mantle compared to the upper mantle. So whatever plume that rising from the denser region as it enter into the less dense region, it will naturally just pounding. So it's like a density or compositional stratifications happen at this step. because there is no known phase transitions that at this depth, at 1,000 kilometers depth. So other than having some density stratifications, it will be very hard to explain why plume just compound at those depths. So with that, I'll conclude, leave it with the conclusion. I don't know if I would like to read through it, but yeah, and here's the reference of this paper, and I guess I'm just going to leave it as the conclusion here and take any questions. So thanks everybody for listening.